Where did we stop in the last class? You're doing the numerical? We had finished center of gravity? Yes. So let me complete the last topic, which is uniform circular motion, and then we will do the remaining numericals. Okay. Let's do it. Where is the other marker? Is there any blue marker? Okay. Let's start with uniform circular motion. Right. See, this is what happens. Uniform circular motion. In short, it is also written as UCM. So, any idea? Anybody? What is uniform circular motion?
When an object is rotated in circular path uniformly.
So, what is uniformly?
At regular
intervals.
Means it is
on same speed.
same speed. Yes, uniformly means same speed. Correct. Now this is correct. Okay. So when an object moves in a circular path with constant speed, right? So object moves. So you say in UCM, in uniform circular motion, object moves in circular path. So articulation is very important, okay? You should be able to write it correctly. Object moves in circular path with constant speed. Right? So this is the first point. Right? What is the other characteristic of a object undergoing UCM? Now see, what is its direction of motion at this point? Along the tangent. Okay? Along the tangent. Here, the tangent is in this side. Out here. So how come it is changing, right? Because at every point, its direction of motion must be changing, right? Correct? Every point, the direction is changing in UCM. So, its direction, it means object's direction. Its direction changes at every instant. Every instant, every point the direction changes, right? So if the direction of motion is changing, then what is happening? Who is changing the direction? Will direction change on its own? Like if the body is moving in a straight line, will its direction change on its own?
No.
Then how will its direction change? Some force must act on it, right? So if this guy is moving in this direction, and now you are saying that its direction is changing. See, if you bring it over here, it is tilted. That means its direction is changed towards left. Okay? So which means at all the points, a force is acting towards the center. Whenever the object is undergoing UCM, okay, it experiences a force which is acting towards the center, due to which its direction changes at every instant. Okay, so the third characteristic is in UCM, the object is governed by a center seeking force or force towards acting towards center. Force which acts towards center. Throughout UCM, in UCM, the object is governed by a force which acts towards center throughout the motion. Is it the compressor of AC? Okay. So in UCM, the object is governed by a force which acts towards center throughout the motion. मतलब यहाँ पे कहीं पे भी, अगर यहाँ पे भी है तो it will experience a force towards center. And because of that force, its direction is changing at every instant. Is that clear? Okay. Can you give me an example where you can experience this kind of a force?
Steering wheel.
Huh?
Steering wheel.
Steering wheel. How?
The car going in circular motion, circular path.
Yeah, I mean, give me some simple example. Let us say you have a small stone tied to a string, and now you're tied it with your finger, and then you're trying to rotate it. So what happens to your finger?
Gets wrapped up.
No, you're not letting it wrap. Let us say it is something like this. You have a knot which is slipping on it. Okay, and you have a stone tied it, like any ring. Okay, so now when you are rotating it, will it be wrapped? No, but what is the experience of your finger? Let's say this is your finger. You will feel some stress, right?
Yes.
Yeah, some tension will be felt. So you will feel that this stone is pulling your finger, right? But ultimately, what is happening? Your finger is pulling the stone towards itself. And that's how its direction is changing at every instant. Isn't it? You will feel that there is a tension in the thread towards you. This object is tight, so it will always be attracted towards the finger. Okay? So this is the force which we call centrifugal force. This force which acts towards the center throughout the motion, this force is called centrifugal force because it is always acting towards the center. It is called centrifugal force. Okay? Or center seeking force. Right? Why did we say that this object direction is along the tangent? Because at this instant, if the string was broken, then you would see that it will now not change direction, it will go straight. Because now no force is acting. Okay? So whatever was its last direction of motion, you would see that the stone would fly in that direction. Okay? So for it to continue to rotate, this string should have remain in place. Is that clear? So you can actually do this experiment. Where will you do this experiment? Close the door, right? See that nothing is hanging on the wall, and use a rubber ball. Okay? Try that. So what will you try? You're revolving it or rotating the ball, and suddenly you leave the string. So you can hold it like this, pinch. Okay, you will feel the pressure at your fingers, and then you release that string. Then you will see when you release the string, the ball will not make circle. It will go straight wherever you left it at the last position. Try it, huh? Gently, without hurting anyone. Okay, so is it understood? Huh? Yeah. So that's your uniform circular motion. Now some examples. Right? What are the examples of uniform circular motion? So the speed has to be constant. So we know that revolution of moon around Earth, is it uniform, or Earth around Sun? Does it take same time to complete the revolution every year? That means its speed is constant, right? These are examples of using. Any other example? Revolution of electrons. So these are all revolution, right? Oh, moon around sun, earth around sun, electron around nucleus. Right? So in the string and stone example, there is this string, and it is the tension in the string which is providing the centripetal force. So centripetal force is the general name given. The force is, like in this case, it is tension, which is acting towards the center. What is the force in case of moon and earth? Gravitational force. Okay, it is the gravitational force which is providing the centripetal force. Centripetal force in this case is gravitational force. Okay, so it is not that it is always contact force. It could be force at a distance. So in case of earth around sun, again it is, what is the centripetal force in this case? Gravitational force. What about electron around it? Yes, it is electrostatic force or the electric force, right? Electrostatic force. So since the charge is moving, don't use static, electrical force. Electrostatic force acts when the charges are stationary. Static means stationary. Electrical force. You can say electromagnetic force, not electrostatic. Alright. So I've given you the example of centripetal force. It changes in different situations. In string case, it is tension. So write this example. Stone. Revolution of stone tied to string. Right? What is the centripetal force in this case? Tension. Okay. So make it a circle. It's looking oval. It should be circle. Which one? There is one very important characteristic that we forgot to mention. Can anybody,
Centrifugal.
in the characteristics of uniform circular motion, its direction changes at every instant. Accelerated motion. So direction changes means what? Its velocity changes. Speed is constant, but not velocity. Okay? So its direction changes at every instant. That is, its velocity changes due to change of direction. Right? So therefore, hence it is accelerated motion. Just add this in this point. Its direction changes at every instant. That is, its velocity changes. Speed is constant, but not velocity. Due to change of direction. Hence, UCM is accelerated motion. So how is it different from uniform linear motion?
Direction changes.
So the direction of velocity does not change.
Velocity is constant.
In uniform motion, the velocity is constant because it is uniform. So neither is it magnitude changing, nor is it direction. So speed and direction both are not changing. So it is uniform linear motion. So is it accelerated motion? No. So that's the difference. Uniform linear motion is an unaccelerated motion. Since velocity is constant. So speed is magnitude of velocity. Okay. So any questions still here? Okay. Now let us discuss the concept of centrifugal force. Concept of centrifugal force. It is also called pseudo force. Pseudo force or virtual force. It's not a real force, okay? Virtual or imaginary force. Okay. We use this concept only to describe a particular situation, right? So let us understand it with the help of merry-go-round wheel. Are you all still writing? Okay, okay, write it then. Once you are done, then I'll explain. All done?
Yes.
Okay. So, see, so again take the example of the string, right? So, let us say this is a merry-go-round wheel. Has anybody experienced it? Trying to ride? Has anybody taken a ride on merry-go-round?
Yeah.
Okay. How was it? Was it a pleasant experience or? Huh? Not very pleasant? Pleasant. Okay. So everybody understands merry-go-round, right? So suppose it has support only at the center. Okay? We have to support only at the center. Now there is somebody. Okay, has taken support of this. Let us say he has tied himself with this support, and now he is holding a some object that is sitting down and holding. I am extending his hand steady. Or there is a thread tied and he is just observing it, let us say. He is just keeping his legs spread and the thread is tied and now he is observing it. Now this merry-go-round is set in motion. So obviously we will make a UCM as we discussed, right? So initially the situation was something like this. Before motion, the string was loose and it was like this. Okay. When the wheel was set in motion, what would we see? You would see that it got stretched and it reaches till here. Right? And this guy has tied himself with the support. So always he is also revolving with the ball. With this whatever is tied. Okay. So how will he see the ball? Always in front of him. And this thing will become tight. This thing will become taut. It's called taut. Straight away. So how do you explain this thing? We will feel that this ball is experiencing force in this direction, which we are calling centrifugal. Right? How this rope is becoming tight? Only because it is being stretched away. That's what he feels. Right? So now let us say it is undergoing UCM and now you have one observer over here. Outside. Okay? What is he seeing? He is seeing that ball is undergoing UCM. Okay? In this direction. He sees the circular motion. So he knows like circular motion is only possible when there is a centrifugal force acting. Okay? So I am drawing a straight line now so that there is no confusion. So the initial state, string was loose. Now when the UCM is taking place, string is taut. And he sees a circular motion, right? Imagine the rim to be the path of the ball. Okay. So therefore for him, the force acts towards the center. Justified? Because for UCM to take place, the force has to be acting towards the center. Otherwise, we have seen a circular motion is not possible. Any object undergoing circular motion has to experience centrifugal force towards the center. It's a rule. So this is a real force, right? So for him also situation is okay, but he is not seeing this ball rotating. He is always seeing the ball in front of him, but it is stretched. Now what happens? This string got broken. Okay. So let us say its direction was along the tangent. So this ball would actually move along the direction of tangent like this. Tangent has to be a straight line. Right? This is the path it would take. Because now the string is broken, there is nobody to pull it towards the center, so its direction will not change. So last direction was along the tangent and this is the direction it would take. Okay? So let us take two different timelines, this and this. So he is happy, now there is no centripetal force acting. So it is traveling straight, right? But at this time, when the ball was here and at this time, right, he is facing the ball only. So for him, earlier if it would have been rotating, the ball would have been here. When it was rotating, the ball would have been here. So what he is seeing? He is seeing that the ball is just going away from him. Okay? What is he seeing? For him, because of the situation in which so ball is going in a straight line for him, which is justified because the only force acting was centripetal force. So obviously now since no force acting, so it is traveling straight along the tangent. But what he feels that the ball is going away from him. So how do we describe? So we say that there is a centrifugal force acting on it, and that is what is taking it away from him. Just to describe the motion to him. Okay? So that's why centrifugal force is an imaginary force. Okay? So since centrifugal force is used only to describe the motion to observer. So motion is not motion is not absolute. It is different for different observer. This is what you should understand, right? So centrifugal force is used only to describe the motion to observer in a certain situation, right? Okay. So it is therefore an imaginary force. But in reality, there is no force acting on it once it is broken from the string. Is that clear? So how much is this centrifugal? But again to explain to him, he always sees the ball in front of him when the string was not broken. Is the ball going away? Is it coming towards him? So it is an equilibrium situation. But we know FCP is acting towards center. He knows. Therefore, he would feel therefore there is also centrifugal force which is acting away of equal magnitude. Okay? Only then this ball will be stationary. Right? It is equilibrium situation for it. So that's why the magnitude of centripetal force is same as centrifugal force is same as centripetal force, but they act in opposite direction. Is that clear? Yeah. So I have explained you the concept of centrifugal force to the best of my ability. Right? So there should not be any confusion now. But it is a imaginary force and its magnitude is same as centripetal force, but its direction is opposite to it. Okay? So you can write FCP is equal to minus of FC. So minus means it always acts in opposite direction to centrifugal force, but the magnitude is same. Okay, so with this let's do balance evaluation. So any desk has two volumes. So unless you have any questions, we'll solve the balance. So have we done all the classwork numericals, page 9, 10? Completed. your notebooks. Did you all try the methods yourself? नहीं, time नहीं मिला. Did we do numerical 4, page 9?
We till 6 till my side.
We did till? अच्छा, 6 तक हो गया है क्या? Very good. So let's try the 7. Question 7. Till 6 we have done completely.
Yes.
So read 7. So we have a uniform meter rule of mass 100 gram is balanced on fulcrum at mark 40 centimeter by suspending unknown mass m at mark 20. Okay. So we have a meter rule. Okay. So let us say you have 0. So whenever there is a meter rule problem, first thing you would do is mark 0, 50 and 100. Right? Then it is written that it is balanced at 40 centimeters. So 40 would be somewhere here. This is where it is balanced. Right? By hanging a 100 by hanging a unknown mass m at 20 centimeters. So this unknown mass is hanged at 20 centimeters. Right? So this is m. Okay. So what is the mass of scale given? It is given as 100 gram. So 100 gram force is acting here. Okay, and m gram force is acting on the left side. Now the scale is in equilibrium. So at equilibrium, what will happen?
Anti-clockwise movement is equal to clockwise movement.
Correct. So at equilibrium, so what is anti-clockwise movement? M gram force. How far away is it from the fulcrum? 40 minus 20. Minus 20. 10 centimeters. This is equal to 100 gram force, the weight of the scale. Into 50 minus 1. So unknown, we don't write with the unknown. We don't write the unit with the unknown. M into this. So this will be 20 and is equal to 10. So 1,000 grams. M is equal to 20. So this is 50 grams. So we have to hang a mass of 50 grams at 20 centimeters. Okay? Right? So mass will be 50 grams.
So 100 GS, no? 100 gram force. 20 meters.
Divided by 20.
So 20 meters equal to 100 gram. O into 10.
Okay. So this 50 GF is basically the weight due to M. Therefore, the mass of 50 grams. has to be hanged. Okay. Now, what is the second part of the question? To which side the rule will tilt if the mass is moved to 10 centimeters? Now, in this situation, it is balanced. So, if I move this mass to 10, so what will happen?
Clockwise motion.
Anti-clockwise moment would increase. It will tilt on the left side, right? So, anti-clockwise. The rule will tilt towards M, right? Correct? So in the second case, so will tilt towards M as anti-clockwise moment increases. Why? Because at 20 it is balanced. So when you increase, go towards 10, this perpendicular distance has increased. So anti-clockwise moment will increase. That is the second part of the question. Now what is the resultant moment? What is the resultant moment now? So the resultant moment will be 50 into 10. Only that is the, so resultant moment will be is, what is it? So the only increase in moment is 10 centimeter into 50. 50 ground force into 10. This is plus. This is plus 500 ground force. Because it is anti-clockwise. Okay. Or you can write 500 ground force anti-clockwise. Right? What is the resultant moment? So one part of her. How can it be balanced by another mass of 50 grams? Right? So another mass of 50 grams, where can we balance? So we need 500. So we need minus 500. But we need 500 clockwise. So only one mass is here. The other mass on scale is here. So additional 500 ke liye 50 gram has to be handled 10 centimeter on that side, right? So we will do the job. And 50 gram at 50 centimeter mark. Right? So जब 50 centimeter पे करोगे तो you have 10 here, 10 into 50. Therefore, you have 50 gram force into 50 minus 40. So this is the additional. We are only calculating additional because we have to negate only this. So this will be 50 gram force into 10 clockwise. So actually this is the answer, and 50 gram at 56. Okay, so it is done logically. Because anti-clockwise moment additional was only this much resultant. So this side also I want to counterbalancing. So this side also I want 500 gram force. My mass is 50, so I need it at 10 centimeter only. Okay, that's all. Has everyone understood this? Okay. Next, we have application type questions. So we still have 10 minutes. 10 or 15? 15. Let's see how many questions we can do. So first question should be easy. So we have three identical forces, each of 4 Newton, acting in the directions shown. Now point O lies at the distances shown, right? The perpendicular distance is shown. So we have A, we have B, we have C. Okay, these are the forces A, B, C. All of them are 4 Newton, and this is how A is 0.8 meter, B is 0.9 meter, and C is 0.6 meter. Okay, so these are the distances. Now, what is asked? Which force has the least moment about O? C. Because every force is force, so the smallest distance would be least moment. So first is C. What about second?
B.
B.
Second is B, maximum, right? Now, what is the reason?
Distance increases.
Smallest
Smallest the distance increases.
perpendicular distance. Okay, from line of action. From line of action of force. In case of B, maximum perpendicular distance. Okay? Right? So it is maximum. From line of action of force. Okay, this was easy. What about question 2? This was question 1, application type. Was for application type. Okay. Yes. Who will answer part A? A body is acted upon by two forces, each of magnitude F, but in opposite directions. Okay. State the effect of forces if both forces act at the same point of the body. So let us say you have a body like this, right? And it is acting at the same point, but in opposite direction. What effect it will produce? This is question 2.
The body will stay in rest, won't move because those two forces are equal in magnitude and
Yes.
that's the opposite direction.
Correct. But how can you say it with surety that it will remain at rest? Is the knowledge about its motion given? What if the body was moving with uniform motion? So its state of motion will not change. If it was at rest, it remains at rest. If it was moving uniformly, it continues to move uniformly. Okay. So since it is an equilibrium condition, net force is zero. So what is it? Net force will be is zero. Hence, will torque act on it?
Zero.
Will torque act on it?
No, net force is zero.
No, net force is zero, right? So it is equilibrium condition. So since it is equilibrium condition, therefore body will remain in its last state of motion. If it was at rest, it will remain at rest. If it was in motion, uniform motion, it will remain in uniform. Now, two forces act at two different points of the body at a separation r. Now, this could be let us know the forces are acting in this direction. This is distance r. Now, the forces are acting in this direction, right? But in opposite direction. And here it is acting in this direction. Now, what will happen? Since two equal and opposite forces are acting, it will create a couple. Okay, so couple will what effect it will produce? Rotation, right? So in this case, a couple would act on a body which will cause rotational motion of the body. Okay, so we have already covered all these concepts. The third is also theory question. State the effect of force on stationary rigid object free to move. Yeah, the body will start to move in the direction of force, right? Since it is a stationary free body, so if force is acting on it, it will move in the direction of force. An object pivoted about an axis. Yes, it will start rotating, right? But provided the force direction should be not along the pivot.
It should be at the maximum distance or the distance.
Maximum distance or any distance, but the force direction should not be along the pivot. See, this is question 3, right? If the body is free, if I apply force, it will begin to move in this direction, right? But if the body is pivoted at a point, So let us say the force is applied in this direction. Then too it will rotate. But if the force is, and what is the line? This is the perpendicular. But if the force is applied in this direction, along the line, then it will not. Okay, the force would be away or perpendicular to the, I mean, this line of action should not be along the pivot. That's the only condition. Okay. Because if the line of action is along the pivot, then this point falls on the force. So the perpendicular distance becomes 0. So it will not rotate. Neither it will rotate nor it will move anywhere. Is that clear? So the answer to the second part is it will cause rotational motion. The second part. First, linear motion. In the direction of force. This is the answer. Okay, for the first part and for the second. So rotational motion will take place. Okay. Time for one more question. I think you can solve all this question yourself now. It's not very difficult. Okay. Now the concept should be clear. So question 4. So you have some body here. Right. So the force is acting on it. This is 10 Newton in this direction. And this is 2 meter. And the force is also acting in this direction. This force is 12 Newton. And this is 3 Newton. So this force is producing this. Okay, so both momentum will get added. It is clockwise. What is the resultant torque? So T resultant is equal to, let's take this as F1, this is F2. So T1 is what is the resultant torque? Okay. So this is, assume this is the pivot. So what is C1? 10 into 2 plus 12 into 3. Right? 10 to the 20, 56 Newton meter clockwise. This is the resultant torque. Has everybody understood it? Will the object rotate clockwise or anti-clockwise? Clockwise. So let's quickly do fifth also. You can tell me the direction of tension. You have to only mark the direction. What is the direction of tension? What will be direction of tension? See, this weight, hanging weight, will be pulled by gravity in this direction, right? So that means the block will move in this direction. The block is experiencing tension in this direction. Now weight is still tied to the string, it is not broken. That means this string is holding this block. So on this block the tension is upward direction. So how to draw the tension? Now there will be tension over here also. So it is always away from the support. Okay, it is always, this is a pulley on which it is rolling. So tension direction is always away from the support. Like this spring is now supported here. Okay, so it is away. Or anything hanging from the ceiling, right? Let us say you have a plate here. So it is away from the ceiling, like this, away from this. It's always opposite. Okay, this is the rule you will follow for tension. So mark 4 locations. Okay. Is it time?
Yes, sir.
All right. So try rest of the questions from textbook and volume. And if you have any difficulty, we'll discuss in the next class. Okay. See you.
Thank you. I can make a presentation.
Yeah.